Okay, I think we should start. It's already 7:09. Um, turn on the camera. Okay. And about the uploading of this, the recorded sessions will also be uploaded. It will be in a YouTube channel, and also the links will be shared on a sheet. I don't know how the NPTEL people will share it to you, but they'll be sharing you a sheet where this PPT questions will be uploaded, and also the recorded version of the class will be uploaded. So you can follow that. And the videos will be uploaded on YouTube, so that link will be shared. Okay. So welcome to the week 2, that is the second class of the interactive session. That will be problem solving session for the course of heat transfer, whose course instructor is Professor Sunando Dasgupta of IIT Kharagpur, and myself Kalpita Nath, and I am research scholar at IIT Kharagpur itself. Okay, so first of all, before proceeding to the first question, I want to discuss about, like, we will go through the few things that sir have already taught you in the class, and on which today's problem sessions will be based on what. So you already have learned about critical radius, right? Critical insulation thickness and critical insulation radius. So let us get back to that on a short details. Let me share my screen. Okay. Is the writing pad visible? Anyone? I hope it's visible. So first of all, what we learned about critical insulation thickness. So let us consider if this is a pipe and this is an insulation. So if this is the inside radius and whose inside temperature is T1, and if this is the insulation and this is the outside radius R0, and here temperature is T1 and here temperature is T infinite, and this is the heat transfer coefficient. Okay, so this is a solid rod with the radius have already been told, and temperature, inside temperature is also Ti, and the outside temperature is T infinity with heat transfer coefficient H. So we already have seen in the class that is the heat flow can be written as Ti minus T infinite upon ln R0 upon Ri 2 pi Kl plus 1 upon H 2 pi R0 L. Right? So now we want to know at which point this will be maximum. That is, at which point this heat flow will be maximum. And we have to keep this resistance, like at the point at which this resistance will be minimum, this heat transfer will be maximum. And we don't want that. That is unfavorable condition. So the point at which this heat transfer will be maximum, that radius will be termed as critical insulation radius, and the difference between the critical insulation radius and the inner radius, that will be the critical insulation thickness. Okay, so sir already told in the class that it will be find out by dq dr naught is equal to 0 by that. So if we do that, we'll find out that critical insulation thickness is equal to K by H. But another thing to note here, we can see that there are two phenomena into play. First of all, this is the conduction and this is the convection. So this is the conduction resistance and this is the convection resistance, right? So how initially the heat transfer will increase up to critical radius and then it will decrease. How? So what is happening is that initially when we will add on this insulation layer by layer, so when we will add this insulation, as this is not a plain wall and this is a like non uniform, this is not uniform, like its area is increasing as we will add on, keep adding on the insulation. So what is happening, its conduction will decrease because of the insulation added, but as the area, surface area outside is increasing, so the convection will increase. As the convection will increase, the convection resistance will decrease, and convection resistance will decrease and conduction resistance will increase. But initially this convection resistance is more dominating, that's the decrease of this is more dominating as compared to increase of this conduction resistance, and all overall this resistance will decrease as this convection one is more dominating. So as this resistance is decreasing to heat transfer, so this heat transfer will be increasing. So another way to find out the critical insulation radius is if we minimize this resistance, cause at minimal point, that is when this value will be minimum, this heat transfer will be maximum. Okay, so if we minimize this, that is if we, this is the our conduction and this is our convection, and we are minimizing this. So what we will do, we are minimizing, if R naught is the outer radius, right? So we will minimize, just one second, we will minimize this summation of R, that is the total resistance. So what we will do, we will differentiate this to equal to 0. So this will again give us RC is equal to K upon H. If we find the same thing for sphere, it will be RC is equal to 2K upon H. Okay. So now, let's find out, like for stainless steel, let's suppose there is stainless steel and we are putting on insulation of some kind, like anything on top, like so what we will need, the inner pipe, the what is there on the inner pipe, that what the inner pipe is constituting of, that is important for us, and what is the heat transfer coefficient on the ambient air or any fluid there is present, that is important for us. Okay, so for stainless steel, the thermal conductivity is 15 watt per meter Kelvin, and for here the heat transfer coefficient at 25 degrees Celsius for free convection is 37 watt per meter square Kelvin. For force it will only increase. Okay, so if we will find out, critical insulation radius for that, it will come out to be 15 upon 37, and that comes out to be 0.4 meter, 0.41. So it is like close to 0.5 meter, right? So for stainless steel it comes like that, and for maximum of the practical cases, this critical insulation radius comes out to be 0.5 meter or lower than that. In most of the practical cases, when the people are like creating like an insulation, they are choosing the insulation material, it is beneficial for us to take the inside radius to be greater than the critical insulation radius. Okay, so we tend to take the inner radius greater than this. Okay, but in most of the cases, as critical insulation radius itself is 0.5 meter, so the inner radius, most of the pipe are greater than this one. So the people in general case don't check for this critical insulation radius. But today's main like solving problem or solving session will be based on finding out this critical insulation radius. So let's proceed to the first question now. Okay. So what the first question tells us about, it's if Ri and R0 are the inner and outer radius of a cylinder with insulation layer of some thickness, where K is the thermal conductivity of the insulating material and Hi and H0 are the convective heat transfer coefficient of inside and outside fluid respectively. Choose the correct formula for critical radius of insulation. Okay, so I'll give you 2 minutes. Like you can answer this immediately itself. So kindly unmute yourself and answer the question. Slide is small. Just wait. Is it okay now?
Ma'am, option D.
Yeah. No, it's not option B. Just now I have shown you now. What did I say? What it will be? Which like what are the things that are necessary? First of all, one is thermal conductivity, another is heat transfer coefficient, right? Yeah. Anyone else? Anyone else who wants to answer? Okay then. Okay. So the answer will be D only. So there is nothing to show about. Just what I have said. It will be the heat transfer coefficient of the outer side, that is the ambient atmosphere. So here the ambient heat transfer coefficient of the outside fluid is already given as H naught. So obviously it will be option D. Let us proceed to the next question now. Okay, so what is said? Heat exchanger shell of outer radius 15 centimeter is to be insulated with glass wool of thermal conductivity 0.0825 watt per meter degree Celsius, and the temperature at the surface is 280 degrees Celsius. It can be assumed to remain constant after the layer of insulation and has been applied to the shell. The convective film coefficient between the outside surface of the glass wool and the surrounding air is estimated to be 8 watt per meter square degree Celsius. What is the value of the critical radius? Tell me, whoever have solved this. Anyone? You just have to use the formula that I have already discussed in the previous question.
Ma'am, option B.
Okay. Yes. Correct. Anyone else who is unable to understand? Anyone? What about others who are online? Okay. Let me solve that now. Yeah. Correct. So I'll show how to solve whoever have not solved for them. I hope the writing pad is visible. Okay. So first of all, the critical radius of insulation is equal to K upon H. That is thermal conductivity upon the heat transfer coefficient. So thermal conductivity here it's said as 0.0825 and the heat transfer coefficient is given as 8. So this comes out to be 0.01031 meter. So this comes out to be 10.31 meter. This is in okay. So what are the options? Sorry, this is mm, and option comes out to be B. Okay. So let us proceed to the okay. So about this also, uh, the inner radius is already given as 15 centimeter, and if we will convert this 10.31 mm, 10.31 mm is approximately is equal to sorry is equal it is equal to 1.03 centimeter. Okay, so obviously this is far less as compared to 15 centimeter. So that's why this line is being noted here, that the when the insulation is also added on the outer surface of the pipe, like heat exchanger, there was no effect of the insulation. That is, the heat transfer remains the same. Just because the inner radius itself is greater than the critical radius of insulation. As I've already said in the initial time, that is, if the inner radius itself is greater than the critical insulation thickness, the increase of the heat loss won't be there. So we don't have to think about that. Okay, so we'll read about question number 3 and 4 altogether. So what does this two questions say? A spherical vessel used as a reactor for producing pharmaceuticals has a 10 thick stainless steel wall with thermal conductivity 17 watt per meter Kelvin and an inner diameter of 1 meter. The exterior surface of the vessel is exposed to ambient air, that is 25 degrees Celsius, for which a convection coefficient of 6 watt per meter square Kelvin may be assumed. So what does the first question tells us about? During the steady state operation, an inner surface temperature of 50 degrees Celsius is maintained by, okay, just 1 second, is maintained by the energy generated within the reactor. And choose the closest value of heat loss from the vessel. Okay, so it is easy. First, we will draw the diagram of there'll be one outside temperature of ambient air of 25 degrees Celsius, and there is a inner diameter of 1 meter, and there'll be a the vessel of the reactor will be 10 mm thick. Stainless steel, that is stainless steel wall, right? So that will be 10 mm thick. So we will just add 10 mm to the inner diameter. So that will give the diameter of the outside radius or diameter of the vessel. Then what comes? Let's proceed to the question number 4 so that we can all together draw the diagram. So what does it say? If a 20 mm thick layer of fiberglass insulation, that is K is equal to 0.040 watt per meter Kelvin, that is an insulation is added whose thermal conductivity is 0.040 watt per meter Kelvin and is applied to the exterior of the vessel above stainless steel, that is outside stainless steel, and the rate of thermal energy generation is unchanged. Choose the closest value to the inner surface temperature of the vessel. So I'll suggest you first draw the diagram. What does these these two linked questions say? You write every temperature and then you have to find out the inner surface temperature of the vessel. That is, if the inner surface temperature is TS1, then we have to find out that. That is just the inner surface. Just 1 second. Okay. It's better for me to draw the diagram for you. Just let me share the screen. I'm drawing the diagram for this question so that it will be easy for you to solve. So first, this is R1, this one is R2, this is stainless steel, right? And this is the insulation. Its thermal conductivity is 0.04 watt per meter Kelvin, and this stainless steel wall is 17 watt per meter Kelvin. Let us consider this as kW. Okay, so inside heat is being like energy is being generated from the pharmaceuticals, and this, let us consider this as outer radius of insulation, and let us consider this temperature to be TS1. Just 1 second. Okay. Okay, so let us consider this temperature to be Ts1 and this temperature to be Ts2, and there will be outside temperature of T infinite, right? And T infinite is already given as 25 degrees Celsius, and heat transfer coefficient is also given as 6 watt per meter square Kelvin, right? Air is there, this is of air, right? Okay, so R1, let me write here, R1 is given as 0.5 meter, R2 is given as 0.51 meter, and R3 is given as 0.53 meter, cause insulation is 20 mm, right? So now what we have to find out, let us check again. We have to find out on the first question, the closest value of heat loss from the vessel. What is the heat loss that is found out from the vessel? So from the diagram, we can clearly balance the heat equations and we can find out how much heat loss is there from the vessel without the insulation. On the first question, insulation is not there. So on the first question, when we will be finding out heat loss, we won't be considering the insulation. For the second question, 20 mm thick layer of fiberglass insulation is been added, whose thermal conductivity I have already included in this diagram, and it is applied, and the rate of thermal energy generation is unchanged when the insulation is being applied. Why? Because the inner radius is greater than the critical insulation radius, right? That we have already discussed in the previous question. So choose the closest value of the inner surface temperature of the vessel. This is relatively easy. In the same way, you will find out, you will balance the heat equation and you can easily find out the temperature. That is TS1 you need to find out, right? Okay. So let's get on with this and solve, and whoever will be solving, kindly tell me. The question is also visible to you. You can pin the question when you want to check the question, and you can pin the diagram when you want to check that. Or you can pin both of them at the same time. First, I'll display question number 3 for your convenience and solve this, then we will go for question number 4. Remember, for question number 3, insulation is not included. So without insulation, we will be solving the heat transfer. Anyhow, if you will be considering that or not, the heat transfer remains same. Okay. Kindly you write the assumptions that are being included in this question. Anyone is having any doubt? You can unmute yourself and ask me.
Ma'am, is the answer option C?
Okay, C. Yeah, for the first one is option C. Should I click to the next question? Yeah, I have displayed question number 4. You can now solve this.
Ma'am, can you show the first slide of that question, like where the general information is given?
See, I want to give one information is that your attendance will be taken every day. So it's not that only you can watch the recorded session, you have to be on the class itself. Whoever is not there, you please pass the information on to them. So attendance will be taken every day. So please make sure that you all are present in all the classes.
Can you show the question number 4? Ma'am, is the option second. B. Option B.
No, it's not option B. Check once what you have, where you have gone wrong.
Yes, ma'am.
Anyone has solved for question number 4?
Ma'am, the inner surface temperature, that will be like which temperature? TS1 or TS2?
TS1. We have to find out TS1. You don't need any, like, to find out anything. You can directly find out from the outer temperature the inner temperature. The middle temperature is not required at all.
Okay, ma'am.
Okay. Let's proceed to the solution then. Okay, let's us first talk about the. Okay, Shanchita, can you tell me what assumptions have you taken? One or two will do fine.
First, the thermal energy generation is unchanged.
It's
So,
already, yeah, it's already said. Like, what assumption have you taken for solving this?
then my assumption, like the values you are asking.
No, 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 not the value. Assumptions. There'll be some initial assumption, no? Like here we are taking steady state because here no mention of temperature is there. Or sorry, time is there, right?
Yes,
So we are
yes, ma'am.
using steady state here. Then, okay, let me write. First of all, we'll be taking steady state. Then one dimensional, cause there is only one dimensional flow. If
Yes,
we'll
ma'am.
consider this r direction, yeah, only r direction. There is no flow in theta direction or z direction. One dimensional. That is radial, right? Radial conduction. Properties are constant, that is density and everything are considered as constant. We have assumed that constant, non-varying. Negligible resistance of contact. Okay. This is not that important though. You may or may not write this. Then, due to low emissivity of stainless steel, we are not considering radiation, right? Though everybody will radiate, there will be radiation inherently. Okay, so but we are
Yes, ma'am.
considering here only conduction, right? Conduction and convection. We won't be considering here any radiation.
Yes,
Okay, no, nothing more is required. So first of all, from an energy balance performed at the instant for a control surface about the pharmaceuticals, see here energy will be generated and everything will be moving out, right? As
yes, ma'am.
heat flux. So the energy generated will be moving out. So the first case, that is question number 3, there is no insulation we have considered. So what they wanted us to find out, let's proceed to question number 3 first. So as they said, closest value for the heat loss from the vessel. So this will be, just one second. This will be is equal to Q. It's way too late to enter to the class. It's already 8. You should come at least up to 7:15. Okay. So TS1 minus T infinite. TS1 is the inlet temperature and that is, this is the TS1, the inside temperature, and T infinite is the outside ambient temperature. We are not considering the middle portion. It's not required. So we'll be considering the whole resistance, right? So this will be 4 pi kW 1 upon R1 minus 1 upon R2. This we already know for conduction, and then the convection part comes 4 pi R2 square H. So here it's 50 minus 25 degrees Celsius, 1 upon 4 pi 17 watt per meter Kelvin, 1 upon 0.50 meter minus 1 upon 0.51 meter, right, plus 1 upon 4 pi 0.51 meter whole square, 6 watt per meter square Kelvin. Okay, so now this is the outer radius, cause on the first case again I'm saying no insulation is considered, so we won't be considering this one, this whole insulation. So there are two radius we are considering, first 0.5 and then this stainless steel thickness, that is 0.51 meter. Don't get confused. So here TS2 is not even present, cause the outer surface of this stainless steel is itself in contact with the outer atmosphere. So here TS2 doesn't come into picture. Okay, so if we will solve this, we'll get as 25 degrees Celsius, 1.84 into 10 to the power minus 4 plus 5.10 into 10 to the power minus 2 Kelvin per watt. This is 489 watt. This is option number C. Okay, now let's proceed to question number 4. So what's it said, that a insulation of 20 mm thickness is added to the to the outer side of the stainless steel wall, and the rate of thermal energy generation is unchanged. Okay, so Eg dot will be same. Choose the closest value to the inner surface temperature of the vessel. That is again, this only we need to find out, TS1, right? TS2 we don't need to find out. So what the equation will be, we know that Q is equal to, 1 second, we know that Q is equal to TS1 minus T infinite upon total resistance, right? So TS1 we can write as T infinite plus Q, and the resistance is 1 by 4 pi kW 1 upon R1 minus 1 upon R2 plus 1 upon 4 pi Ki. What is Ki? This is the insulation thermal conductivity. This one, insulation thermal conductivity, that is 0.04. So we are just considering the resistance of that, because that layer is also coming into consideration now, which was not considered in question number 3. So this will be 1 upon R2 minus 1 upon R3. What is R2 and R3? This radius is R2, that is up to the stainless steel wall, and R3 is the radius, the total radius up to insulation, right? So R3 is 0.53 meter and R2 is 0.51 meter. Then plus again 4 pi R3 square H, cause now the ambient temperature is just outside the insulation. Earlier it was just outside the stainless steel layer, so that's why it was 1 upon 4 pi R2 square H. R2 means the outer radius of the stainless steel pipe. But in case of insulation, when insulation is added, this outer radius becomes now, that is in contact with the ambient temperature, is the insulation thickness plus the radius of the outer side of the stainless steel pipe. So this will be actually will be considered in that when we will be taking the convective resistance, right? So that's why we have written here 1 upon 4 pi R3 square H. So this is the total resistance. So what we will write here, TS1 is equal to 25 degrees Celsius. This is the T infinite, that is the ambient temperature, 489 watt. This is Q, we already found out from here. Obviously the heat remain unchanged as it is already said, that is the energy generation, and we have already found out the energy generation is equal to the heat flux, right? So this will be same. So here Q is 489 watt, and then comes the whole resistance that is there in the picture. So 1.84 into 10 to the power minus 4. This is the first part. This one we have already calculated earlier. Here 1.84 10 to the power minus 4. This just we have put here. So the next part is 4 pi 0.04 into 1 upon 0.51 minus 1 upon 0.53. That is R2 minus R3. Right, plus 1 upon 4 pi 0.53 whole square, because here now it is R3 into 6. What is 6? The length of the pipe. Length of the pipe is already given as 6 meter. Okay. So now this whole is in Kelvin per watt. This resistance, okay, this whole resistance is in Kelvin per watt, and this is in watt. So this cancels out and this becomes in Kelvin. Now if we will calculate all of this thing, it will come out to be 120 degrees Celsius. What is this? This is option number A. Any doubt regarding this? Anything that you are not able to understand? It's okay, right? You've understood?
Yes.
Okay then. Okay, then anyone else who is having doubt? Okay, then without further ado, let us proceed to the next question. This is relatively easy. So, question number 5. So, which of the following dimensionless number gives an indication of the ratio of internal conduction resistance to the surface convective resistance? Who will be able to answer this?
Option A.
Yeah, it's option number A. Okay. Next, let's proceed to the next question. Nothing to explain here. This is question number 6. I'll decrease the size a bit because it's not visible. Yeah. A high temperature gas cooled nuclear reactor consists of composite cylindrical valve for which a thorium fuel element, that is K is equal to 57 watt per meter Kelvin. There is thermal conductivity of thorium fuel element, is encased in a graphite that is of thermal conductivity 3 watt per meter Kelvin, and gaseous helium flows through an annular coolant channel. There is a coolant channel. Through the coolant channel, the gaseous helium flows. What is coolant channel? It will decrease the temperature cause internal heat is being produced, right, from the thorium material. Consider conditions for which the helium temperature is T infinite equal to 600 Kelvin. So, and the convection coefficient at the outer surface of the graphite is H is equal to 2000 watt per meter square Kelvin at the outer surface. Okay, so here for the coolant, as it is a fluid, it is helium, right? So its heat transfer coefficient is given as 2000 watt per meter square Kelvin, and also its temperature, the temperature, ambient temperature, this is considered as ambient temperature, and this is given as 600 Kelvin. So we can find out the convection heat transfer from there. If the thermal energy is uniformly generated in the fuel element at a rate of Q is equal to 10 to the power 8 watt per meter cube. Choose the correct value of temperature T1 and T2 at the inner and outer surface respectively. From the diagram, it's clearly visible which has been considered as T1 and T2. Inner and outer surface of the fuel element, that is the thorium. So, what will be the temperatures? These are some information that will be required to solve this question. Okay, let me explain this a bit. The heat per unit length may be determined by applying an energy balance to the control surface of the fuel element. Fuel element means the thorium part, this one where the heat is being generated. For if we consider this at the inner surface as the adiabatic surface, we can use this following equation, where Q dot is the heat generated in that thorium element. This can be used in your equation. That is, what is Q dash? Q dash is the heat flux that is going out of the from the inside, from this thorium element to the outside layer. So heat generation is already given as 10 to the power 8 watt per meter cube. We can use that. And with zero heat flux at the inner surface of the fuel element, if we consider zero heat flux, that is obviously the heat flux will only be generated because of the heat generation here, and heat is only generated in the fuel element, that is the thorium. So that's why there will be zero heat flux on the inside. So this equation can be considered for the fuel element that is generating the heat. So here for the heat generation, this equation can be used, that is T1 is equal to T2 plus this. So this T1 is equal to T2 plus the expression that is given, that can be used. So every value is given here. You can just use all of that to solve. And what is this KT? KT is for the thermal conductivity of this thorium, right? That is the heat element. This is the KT here. And R1 and R2, everything is indicated here. You can use them to solve. Okay. Solve this now and tell me what the answer will be. I'll give you 5 minutes time, and I'm coming back in 3 minutes. Anyone is having any doubt? Before I go, I should answer that. Anyone is having any doubt?
No, ma'am.
Okay, then you guys solve. I'll come back in 3 minutes. Hi, anyone have solved? Anyone have solved, or should I give you any hint? Diagram is also given. Yeah, someone wants to say something? Okay. You can try. I may give you some hint. Okay. So first of all, what you will do, the outer surface temperature of the fuel, that is the T2, right? Yeah, T2. T2, we have to find out from the heat rate equation. That is, we know that Q dash is equal to T2 minus T infinite by R total. That is the total resistance. Okay. So R total we can find out. Everything is given here. That is total radius along with the insulation and the mid layer. Everything we can find out the total radius. So from there we can get this equation. And now I have already given this equation, right? So if we will consider the interior surface of the element is essentially adiabatic, so that means there will be no heat transfer from the heating element, that is the thorium, in the inner side. That is, there will be only heat transfer on the outer side. So the heat flux we will only consider from the heat generating element to the outer side. That is, we can use this equation, this adiabatic surface equation here. So Q dash we can find out from Q dot by R2 square minus R1 square, right? So Q generated, the heat that is generated is already given. It's given in the question as 10 to the power 8 watt per meter cube. So we can use this, and R2 R1 we already know. We can find out this. So if we find out this, then using this equation, this from here, we can get up to here and we can find out T2. T2 as Q dash R total dash plus T infinite, right? So Q dash we can get from here, we can put it here, right? And from there we can get T2. So T2 we can get. Once we will get T2, we know that one side temperature of the heating element. Now, with zero heat flux at the inner surface of the fuel element, that is, we have already said, we have considered that surface to be adiabatic. That is, which surface we are talking about? Let me make you clear about that. This surface, that is T1, the surface beyond that on the inner side. So we are considering this wall where the T1 temperature is there, this wall to be adiabatic. So there won't be any heat flux inside. There will be only heat flux outside. That is, from this heat element, this heating element, the heat will only flow to the outer direction, right? So, sorry. So if it is that, with zero heat flux at the inner surface of the fuel element, we can use this equation that is already given. So from this equation, we can find out T1 as T2 plus some function is given. So everything, this heat generation also we know, this R1, R2, everything we know. This is thermal conductivity of thorium, we also know that. From the previous equation, like this problem, it's already given the thermal conductivity of this fuel element, that is the thorium fuel element. It's already given as how much? It's 57. right? It's given as 57. And this R1, R2 we know. This heat generation from the thorium element is also we know. So we can find out this T1 from here. So T1, T2, this information, like only this we want to find out in this question. So now will you be able to solve? Anyone? It's very simple. First, we have to find out Q dash from Q dash equation. That's the main heat equation that we already know. This Q dash we need to find out from Q dot, that is the heat generation from the thorium element, and from here we can find out T2 from this previous equation. T2 with respect to Q dash. So this T2, that is the outside temperature of the heating element, we found out, and from the equation that is already given. Let me open this. The equation is already given here. From this T2, we can find out easily T1. So T1, T2, these are the things that we need. Will you be able to solve it now? Anyone? Okay. Okay, then you people solve. I'll give you 5 more minutes to solve this. And then we have how many? 5, 6 more questions to go with. But those are simple questions. We will solve one question on lump parameter model. We will discuss about some basics that already been taught on the class. So yeah, you first solve this, then we will proceed. Cause we need to clear everything about the this conduction. Cause from next class we'll be solving the later parts. Okay, so I'll give you 5 minutes. You solve fast. I'll come back. Have anyone solved? I've given you 10
Just a
minutes.
minute.
Huh? What?
Just a minute. Only little calculation is there.
It's okay. Actually, we have more questions to solve. So it's already, we have given 25 minutes on this question. Make it fast.
Then can you show the options?
Okay.
Option B.
Let me check. T1 is 30. No, it's option B. Okay, there must be some calculation mistake. Just wait. Okay, let me show you how to solve this. Okay, should I proceed?
Yes, ma'am.
Someone has answered something like this. It's D. No, no, it's not D. T1 will come as 938. That is, it will be option B. Oh, just wait. Option B. Just wait one second. Yeah, it's option D only. Correct. It's option D. I have not checked for T2. It's option D. Okay. Then you guys are correct. So you have like understood only, but then also let me solve it for you. Okay, as I've said, first Q dash is T2 minus T infinite, R total. So first what we have to do, we have to find out R total. R total is ln R3 upon R2. 2 pi K plus 2 pi R3H. Okay, this, just one second. This K is for graphite. Okay. So what this will come? This will come as ln 14 upon 11 2 pi 3W mk plus 1 upon 2 pi 0.014 meter 2000 watt per meter square Kelvin. Okay, so this will come out as 0.0185. I think you all have gotten this only, because after that, as we already said, the inner surface is adiabatic, so we can use the equation that is provided. So it will be q dot pi r2 square minus r1 square. So this will be 10 to the power 8 watt per meter cube into pi 0.011 square minus 0.008 square meter square. So this will come out as 17907 watt per meter. Okay. Now we already know that q dash is equal to T2 minus T infinity by R total dash. So T2 is q dash R total dash plus T infinite. Okay. Now this is, we already found out q dash as 17907. So we will just use this. Watt per meter 0.0185 meter Kelvin per watt plus 600 Kelvin. Okay, this came out to be 931 Kelvin. So this is T2, right? So T2 is 931 Kelvin, but we cannot, like, if we will do elimination method from, we will always, for any question, we will try to find out one value if two values are asked, and we will try to do the elimination method. That is, from the options, we will check which of the option is valid for this. So from here, we have already found that option A and option D is on the picture. Option B and C is already eliminated if our calculations are correct. Then option A and D, we must find out T1 cause like there are two options where T2 is 931 Kelvin, right? Otherwise, we would have just selected the T2 where it was 931 Kelvin. I hope you have understood. So as both of the both of the options have T2 as 931 Kelvin, we have to find out T1. So for T1, it's already given the equation that's already given as this whole equation. So if we will just put every value here, so it will be 931 plus 10 to the power 8 watt per meter cube, 0.011 meter whole square upon 4 into 57 watt per meter Kelvin. So this is 1 upon 0.008 upon 0.011 whole square minus 10 to the power 8 watt per meter cube, 0.008 meter whole square, 2 into 57 watt per meter Kelvin. If anyone is having any doubt what I am writing, like if you are not able to understand, please interrupt me and ask. 0.011 upon 0.008. Excuse me. So T1 is 931 Kelvin plus 25 Kelvin minus 18 Kelvin. So this is 938 Kelvin. So which one of the option is having 938 Kelvin? That is D. So answer is option D. Okay. Now, before proceeding further, we would like to, like, the next one or two question is based on learned parameter model. So we will revisit the learned parameter model once more. So what is learned parameter model? For learned parameter model, we assume that the temperature of the object will not change with space, but it will change with time. And we also have found that is a temperature difference T minus T infinite, that is the center temperature and at time T to the ambient temperature, and Ti, that is the initial temperature of the body, and this will be the ambient temperature. This sir have already explained how to derive this equation in the class. So this will be exponential minus HAS upon rho VC. Who is coming now? Just one second. Class will be ending in 15 minutes more. You should come earlier, no? Let me. From the next day, I'll be accepting the attendance earlier. Like if anyone will come this late, I won't be accepting the attendance then. Who is this, Shaili? Yes, I've already taken, but two people have just, like, one people have just joined. I don't know why that person have joined now. It's Saili, right? But that person have already left. Joined and left, so I won't be considering her attendance. Whoever that may be. Okay. Okay, let's continue that. So for learned parameter model, this is the main equation, and another thing that we want to know about is like here, this one, this whole thing is just the thermal time constant. Okay, I think sir have already taught this. So this is HAS. So this is the thermal time constant, and this is 1 upon tau T, thermal time constant. So this we can write as HAS into rho Vc. Okay, so this is RT, that is the thermal convective resistance, and this is termed as CT, that is the lumped thermal capacitance of solid. Okay, and another thing that we want to revisit is the Biot number. The Biot number is equal to HL upon K. If we will rearrange this, it will come as H upon K by L, that is 1 upon K by L and 1 upon H. That is, this is the conduction resistance and this is the convective resistance. R conductive and R convective. That is, if R conductive is far greater than R convective, sorry, R convective is far greater than R conductive, then Biot number is small. And we know that for the lumped capacitance model, Biot number should be small. So with that thing into mind, we will proceed to the next question. Choose the correct range for which the lumped parameter analysis for transient heat conduction is essentially valid. Which of the option is correct? Anyone who wish to answer? Unmute yourself and answer that.
And option B.
Correct. So this is option B, 7. Then let us proceed to the next question. A pipe of outside radius 20 mm is to be insulated with asbestos, which has a mean thermal conductivity of 0.5 watt per meter degree Celsius. The local coefficient of convective heat to the surroundings, that is the heat transfer coefficient, is given as 10 watt per meter square degree Celsius. Find the critical radius of insulation for optimum heat transfer from pipe. What will be the critical radius of insulation? This is relatively very simple question. It will just require 20 seconds to solve. Tell me what will be the option?
C.
Yeah, option C. So this is option C. Then next question. Biot number is an essential dimensionless number to assess the applicability of the lumped capacity model to a particular system. Right. For the specific case of a large Biot number, it can be said that the convective resistance dominates. Is it true or is it false? I've just said true. It's true. How? What is Biot number? What is Biot number? I've just said no. What are the ratio of resistance that constitute the Biot number? Which resistance upon which resistance?
Conduction resistance while convective resistance.
So then what it said, convective resistance dominates. If convective resistance dominates, then convective resistance is more, and convective resistance is in denominator. That is, Biot number should be small if convective resistance will dominate.
Yes, ma'am.
So then what makes the answer of this question?
False.
Yeah, correct. It should be false. So this is option B. These are relatively simple questions, right? Next one is also pretty simple. Suppose that a hot metal ball is suddenly immersed in cold water. What will be the condition for the ball to maintain it at uniform temperature? What will be the answer for this? The conduction resistance in a ball should be very large compared to the convective resistance for heat transfer from the surface of the ball to water. Or the conduction resistance in a ball should be very small compared to the convective resistance for heat transfer from the surface of the ball to water. Or the conduction resistance should be equal to the convective resistance. What will be the option? Anyone?
Ma'am, B.
Huh? B.
Yes, ma'am. Second option.
Yeah. It's correct. So, as already said, that convective resistance should far greater than as compared to conductive resistance always for Lunt parameter model to be valid. So, it's option number B. Okay. So, last two questions. The question number 11 is the roof of an electrically heated home is 6 meter long as is given in the diagram, 6 meter long, 8 meter wide and 0.2 meter in thickness, and is made of a flat layer of concrete whose thermal conductivity is 0.8 watt per meter degree Celsius. The temperatures of the inner and outer surfaces of the roof one night are measured to be 15 and 4. That is, the ambient temperature is 4. For a period of 10 hours. Determine the rate of heat loss through the roof that night and the cost of heat loss to the homeowner of the cost of electricity. If the cost of electricity is 0.08 kilowatt hour, then from that we can find out the cost of heat loss. Anyone who can solve? It's very easy. It's based on the first class, first initial lectures. Just keeping to note that here only conduction is taking place, right? As no heat transfer coefficient is given, only thermal conductivity is given. So here we will only consider conduction. Anyone is having any doubt regarding this question?
Ma'am, are there options to this question?
No, there are no options. You just need to directly give the answer. Okay, I'll give you 2 minutes. You answer this. I'll be back. I have to take a call. I'll be back in 1 minute. Has anyone solved it?
Ma'am, the answer for bit number A is 0.4048 kilowatt.
How much?
0.4048 kilowatt.
0.4. No, 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 no. What have you taken? Like here, K is given as zero point 0.8 watt per meter degree Celsius, right? Have you
Yes, ma'am.
considered area? First, you have to find out the heat. Yeah, 1.69. Correct. Okay, let me solve this then. I think you have just taken flux. You have to take the heat, total heat, rate of heat
Yes.
loss. So, okay. So it will be simple. It will be Q dot is equal to K A T1 minus T2 upon L. So K is given as 0.8 watt per meter degree Celsius. And the area is given as 48 meter square. And T1 is given as 15 minus 4 degree Celsius, T1, T2, and 0.25 meter. L is 0.25 meter. L means the thickness. So it is just considered as plain wall, nothing else. It's relatively very simple. So it is 1690 watt, that is 1.69 kilowatt. For the second part, anyone? Anyone? See, here heat loss you have already found out, and time is given, so you have to find out the power. And for power, it's given as the amount that is required per unit power that is lost. So how much will be the total money that will be cost by the owner? Anyone who can answer?
1.35.
Yeah, correct, 1.35. Yeah, so how come we will solve this? This is Q as Q dot delta T, that is 1.69 kilowatt into 10 hour, total 10 hour, right, for which it is lost. So 16.9 kilowatt hour, this is the total power, total energy. So then cost is per unit energy, it is 50, sorry, 0 point, just one second, it's 0.08 dollar per kilowatt hour. So this is 16.9 kilowatt hour. So this comes out to be $1.35. Okay, now we have 3 more minutes, but yes, we have one more question and we will solve this and then we will end the class. So the last question is, a common way of measuring the thermal conductivity of a material is to sandwich a electrical thermofoil heater between two identical samples. Okay, these are the two identical samples that is given in the diagram itself. The thickness of the resistance heater, including its cover, which is made of thin silicon rubber, is usually less than 0.5 meter, the thickness between the two samples, right, at constant temperature. The thickness is given. The lateral surfaces of the samples are well insulated, so there will be no heat loss from the sides. And wait, there is well insulated to ensure the heat transfer to the samples in one dimensional. That is only in Z direction there will be heat transfer. Okay, so two thermocouples are embedded into each sample some distance L apart. Okay, and the differential thermometer reads the temperature drop as delta T. Okay, and then the distance along each sample. When steady operating conditions are reached, the total rate of heat transfer through both the samples become equal to the electrical power drawn by the heater. Okay, the total heat transfer through both the samples become equal to the electrical power that is drawn by the heater. So we have to find out the heat transfer, which is determined by multiplying the electric current by the voltage. So the power total power that is given, we can find out that, and from that we can find out the flux, because these are equal. In a certain experiment, cylindrical samples of diameter 5 centimeter and length 10 centimeter are used. So sample length is given. So from there we can find out the distance. The two thermocouples in each sample are placed 3 centimeter apart, and after the initial transience, the electric heater is observed to draw 0.4 ampere at 110 volt. From that we can get the power. And both differential thermometers read temperature difference of 15 degrees Celsius. Determine the thermal conductivity of the sample. Simple, it's very simple. The same equation will be used for the conduction. No convection is going to be used here. So we have to find out the thermal conductivity. Solve this. If you are having any doubt, then ask me. Can you tell me how we are going to solve this? Just check that the heating element is in between. So whatever heat flux will be there, that is the heat will be transferred in both direction, like in both of the samples, because the heat insulation is there from the sides only. But in the Z direction, there will be transfer of heat. And once first we have to calculate the power from, cause here the ampere, that is the current, and the voltage is already given. From there, that we can consider the power. We can find out the power, and from power it is already said that it is equal to the heat flux, right? Not heat flux, basically the heat that is transferred. So we can find out that the heat transferred, and from that by calculating the area, all the dimensions are given, we can calculate the area. And if we calculate the area, then we can clearly find out the K, that is the thermal conductivity. I have already given you the roadmap how to solve this. I'll give you 2 more minutes because it's already 9:02, and you give me the solution. Anyone? See, the thickness of heater is also given, and the sample's diameter length is also given. So you can clearly find out the area. That is, what is the area that will be applicable here? It will be the area from which the heat will be flowing, right? That is the area between the sample and the heater. That will be our main focus. So if the sample is a cylinder, so you can understand what will be the projection area. That is what will be the area that will be used for the heat to travel.
So is the answer 195.55?
Which one? Which answer? The final thermal conductivity? No, no. I think you have gone somewhere wrong. Just check once. See, it's there are two thermocouple in each sample, and it said that the distance between the thermocouples is 3 centimeter, right? That is, the thermocouples are placed 3 centimeter apart, and the differential thermometer read a temperature drop of 15 degrees Celsius. So from there, what you can find out, tell me. This is the distance and temperature difference. So you can clearly directly put it there. Anyone? Anyone who wants to answer? Anyone wants to answer, or should I proceed with the solution? Because it's way too late. It's already 9:08. 22.4. Let me check once.
Ma'am, 22.4.
Yeah, it's 22.4. Okay, you have got the answer. Then let me proceed with this final question solution. Okay, so it's question number 12. It's relatively simple. It's just said in a twisted way, but whatever the question may be, anywhere, you just simplify it. You just link up with the basic equations, what is given, what values are given, and how we can link with which equation we can link with. Just link with that and just simplify that. That is the main way of solving these questions. So first, it said that power is voltage into current, that is 110 volt into zero point 0.4 ampere. This is the current. This is 44 watt. Now, it said that the heat flow is on both the direction, right? So for one sample, if we will calculate in one direction, because we just have to calculate the heat in one direction, and we have to compare there, right? Because we have to find the thermal conductivity. So one direction will suffice. So for one direction, it will be half. So this is half into 44 watt. So this is 22 watt. Now we have to find out the area. So that will be 1 by 4 pi d square, because it said it is cylinder. And obviously, if this is straight cylinder, then the upper direction is just a circle, and that will be in contact with the resistor, right? That will provide the heat. So this is 1 by 4 pi. The radius, sorry, diameter is 0.05 meter whole square. This is 0.00196 meter square. Now, it said that the temperature drop, that is delta T, is given as 15 degrees Celsius for the distance of from thermocouple. It's clearly notified, that is the distance between thermocouple is 3 centimeters. So we can use that information. So by that we can find out Ka delta T by L. Right. So K is equal to Q dot L by A delta T. Now it is 22 watt and 0.03 meter. Right. This is 0.03 meter. And this is 0.00196 meter square and 15 degrees Celsius. So this comes out to be 22.4 watt per meter Celsius. Okay. Anyone is having any doubt? Okay, then let us end today's class. I'll meet you all next week, same time, that is at 7 p.m. On Tuesday. Okay, then. Bye, guys.
Thank you.
Welcome.